All right, welcome to another lecture about physics. This is going to be the last lecture in this part of the course, so wrapping up our discussion of mechanics, or how things move generally. And we're going to wrap it up with projectile motion and talk a little bit about satellite motion, or orbits. All right. Okay, so before we start talking about projectiles, we do have to update our understanding of vectors just a little bit. And the reason being is that so far, when I've told you about vectors or shown you things having to do with vectors, we've really only dealt with vectors that are purely horizontal, meaning they're pointing left or right, or purely vertical, meaning they're pointing up and down. You probably could imagine that there are vectors, a great many other vectors besides that, that don't just point to the left or to the right, or point up or point down, but they point to the side, at an angle, at all kinds of angles, right? And even that's just in a 2D, right, just in a flat surface. There's also angles that point out, point all the way around. So there's this whole three-dimensional thing going on that we haven't really touched on. We've kind of only talked about binary, left and right, or up and down. So yeah, so those are the kind of vectors you were looking at before. And the good thing is that we're still only going to talk about 2 dimensions, so up, down, left, and right. But it turns out that all vectors in that up, down, left, and right, that 2-dimensional plane sort of world, are made up of some amount of vertical component and some amount of horizontal component. So we kind of already have the machinery to think about any vector we want in terms of its vertical and its horizontal components, or how much that vector points vertically and how much it points horizontally. So as an example, we have, say, like a vector indicating an amount of force. Right? Force is a vector. I can draw an arrow to indicate that amount of force. And remember that, you know, the direction is the direction the force is being applied. The length of the arrow tells you how large the force is, the amount of the force. So if you have a vector, it's pointing off at this like upwards and to the right sort of angle. Like I said, it turns out you can always think about vectors in this plane as being made up of vertical and horizontal components. So the way that you do that, or you figure out how much of that vector is vertical and how much is horizontal, is, well, there's a lot of ways to do it, but one way is you imagine projecting this vector onto a horizontal sort of line and a vertical line and a horizontal line. Right? So if I take my force vector, right, it's pointing off like this, then if I want to figure out what the vertical component of that force is, I imagine like a line or a wall, sort of vertical wall that hits up with the base of that force vector. And then imagine shining a light straight at that force vector. Right? So if you shine at the force vector, that vector, that arrow, is going to cast a shadow on our wall here. And the height of that shadow, right, that's, if it comes straight, the light comes straight at it, it's going to cast this shadow like right here. The height of that shadow is the vertical component. That's how much of that force is vertical. Right? So in this case, we're showing a little dotted green arrow. That's how much of the force is vertical. And then the same sort of thing is if you take that force vector again and you instead imagine a kind of floor, putting a floor underneath it, a horizontal floor, and you shine a light directly downward onto that floor, you're going to cast a shadow, right? Cast a shadow, and the length of that shadow is the amount of the force that's horizontal. So just like here in that green arrow right there. Right? So you can do this with any vector. And again, this is only in 2 dimensions, vertical and horizontal. If we get to 3 dimensions, we won't get to 3 dimensions, but if you do go to 3 dimensions, you have like a sort of into and out of this picture. The same sort of thing applies, right? You just project onto that third direction, and you can get all 3 components of the vector. And again, or beyond that, it's not just a force, right? I just used a force vector as an example. You know, any vector can do this. So the vector for an object's velocity, for its momentum, for its acceleration, you know, any vector. Okay. So, why is that important? The main reason that it's important that you can break down vectors into their, say, horizontal and vertical components, and any vector you can do this, is that the components of a vector that are perpendicular, so we have a vertical component is at 90-degree angles to the horizontal component, right? When you have vector or components that are that are perpendicular to each other, those components are what we would say they're independent of each other. So you can change the vertical component, say, of a vector and not affect its horizontal component at all, right? Or you can change its horizontal component and not affect its vertical component at all because they're independent of each other. Or another way of looking at that is that you can, well, I guess not another way, it's the same way. If you, in this picture here, or these, you know, different pictures, you imagine having like a block of stone or something like that, and say you have like a rope tied to the stone and you're trying to pull on that rope, right? You want to drag it along. And say it's a very, very heavy stone, you're never going to lift it off the ground, but you might be able to drag it. So, if you want to drag it along, the only way you're going to actually drag it along is if you apply a horizontal force. Right? The horizontal force is the only thing that's actually going to move the block horizontally. No vertical force is ever going to move the block horizontally. So that's an example of vertical and horizontal components being independent of each other. But beyond that, you can look at just, you know, applying a force. So say like in the upper left image here, you start out, maybe you have a rope attached to this stone, and you're pulling up and to the left. Right? So the fact that these components, these vertical and horizontal components, are independent of each other means that none of that vertical pull that you're doing has any effect on moving this stone horizontally. It's only the horizontal amount that you pull that's actually going to cause that rock to move. And if it's enough to overcome static friction, will cause that rock to then accelerate. So if you move from that picture in the top left, the one below it, sort of going counterclockwise here, then that's a much better application of force. If it's the same amount of force you're pulling, then instead of pulling this up almost like at a 45-degree angle, if you pull almost horizontally, then now we look at the components of that vector. The vector is almost entirely horizontal. There's only a small vertical component, right? Meaning all that force that you're applying, most of it is going into the pulling horizontally, so you're actually going to move that block more, right? Or you're going to accelerate it more. And sort of the other extreme, or keep going in the opposite direction to extreme case, if you pull vertically entirely, right? If you try to pick up, like I said, this stone, you're just not going to pick it up. It's just too heavy, but we could slide it. So if you try to pull this way straight up, that vector now has no horizontal component, right? You try to imagine projecting a light down onto that vector, there's no shadow it makes on this horizontal floor here, right? So that vector is entirely vertical, and there's no way it's ever going to pull the block horizontally. And one more example is just like, not quite as extreme as a vertical one, but if you're pulling almost vertically, again, you can look at the horizontal and the vertical components of that vector, and most of what you're doing is pulling vertically. You're not really pulling horizontally very much. In fact, it might not even be enough to overcome static friction to get that block to move. So yeah, so what you do, or what's vector, the components a vector is made up of, are independent of each other, as long as we're thinking about just horizontal and vertical components. Components that are at 90 degrees to each other. Alright, so why is that important? Here, well, now we're talking about projectile motion. Okay? So projectile motion is essentially like throwing a baseball. And not necessarily thinking about somebody pitching a baseball, because those times they're pitching it fast enough that it almost doesn't seem to arc at all. For the most part, we're talking about, you know, like tossing a ball up in the air, comes back down, or maybe think about underhand tossing it. Any kind of motion like that. And even the baseball, even the pitcher throwing the baseball, it does go down a little bit, but it goes so fast that it's going so fast horizontally that it doesn't drop down very much at all before it reaches the catcher. So right, if you do throw a ball, say up and to the right here, we could draw a vector at any point that represents the velocity of that ball, and just after it leaves your hand, the velocity of that ball might look like that, right? It's going to be, it's moving at certain speed and it's moving up and to the right. There you go. So that light blue vector is the, or arrow is the vector for the stone's velocity, or ball's velocity, whatever it is you're doing. And again, you could imagine if you place a horizontal sort of wall, I keep mixing it horizontal, if you place a vertical wall right at the base of that vector and project that vector onto that vertical wall, then we'll get the vertical component. So that's the that vertical blue arrow is that vertical component of our velocity. And same sort of thing on a horizontal floor, project that vector down and we get, you know, just has a much smaller horizontal component to its velocity. But so now these two things, I don't know if I can, yeah. So that's the vertical component, that's the horizontal component. And together, well, they're components of a velocity vector that looks like that. Right? So that's the picture here. And so projectile motion in general, it combines vertical and horizontal movement. So this is why we need to talk about vectors a little more in a little more detail. And question you can think about now, and we'll get to in just a little bit, is which component of this velocity vector for the stone does gravity act on? Right? Gravity accelerates objects, it acts force on objects, so it accelerates them, meaning it changes velocity. But which of the components will gravity act on? Okay, so now we're going to look pretty in detail at an example of a projectile. And a fairly straightforward one, or even simpler, instead of imagining somebody throwing something up and it falling down, is if you say roll a ball off the edge of a table. So you've all probably seen this. If you roll something or you slide something off the end of a table, it doesn't do this thing where it goes out straight and then falls straight down, or just goes to the edge of the table and falls straight down. If it has any sort of velocity, it arcs as it goes off the side of the table, right? It's going. However, that motion, when it's doing this, initially it has just a horizontal velocity component, but then gravity acts and starts giving it a vertical velocity, actually downward velocity component, and so we end up with this this curved sort of motion, which is a combination of horizontal motion and vertical motion. So, looking at these pictures, say at the top left here, if we rolled this ball off a table and it just, well, there was no gravity, then it would just continue its horizontal motion, and assuming there wasn't friction or anything like that, then it would just continue at the same speed, right? Unless there's no other forces acting on it, it's going to continue moving at the same speed. So these pictures are essentially showing a bunch of snapshots, maybe in equal times, maybe like 1 second or 1/10 of a second. So you see the ball at the first time, and then the second time, the third time, fourth time, fifth time, and it's moving equal amount in each of these times. Right? So that's purely if it was just moving horizontally. If it was just moving vertically, like if it got to the edge of the table and somehow just stopped as it got to the edge of the table and then fell straight down, then we get this upper right picture, which is just vertical motion. And that takes us back to looking at when we talked about linear motion a lot, and we talked about acceleration, or constant acceleration, or free fall. So You release a ball and gravity is accelerating it downwards, meaning it's increasing its velocity. So in the first interval of time, it moves a certain distance, and in the next interval of time, it will have sped up so it moves further. And then the instant after that, or the next time interval after that, it speeds up even more and moves even further in that next time interval. So that's why we get this ever-increasing distance adding up here. And essentially, that projectile motion, when you roll this ball at the edge of the table, we just combine both of those motions, and this is what we get. We get this arc, we get this parabola technically, right? Which is, you could call a superposition of the horizontal and vertical motions, just a combined version of them. So, just to be very clear, we're going to look, like I said, we're looking in detail at this. So, again, thinking about that uniform or that horizontal motion, uniform horizontal motion meaning motion with a constant velocity. So imagine again we're rolling this ball, and if it's in uniform motion, it means it's moving at a constant speed, and a constant speed means in the same time intervals it's going to move the same amount. Right? If it's moving at 5 miles or 5 meters per second, then in every second it moves 5 meters. Right? That's just what speed means. So this picture just showing you, picked 1 second as the time interval. It could be any time interval, but it helps to just pick an actual time interval. So after every second, the ball will have moved an equal distance. So at 0 seconds, it starts here, but it has some velocity. So 1 second later, it moves to there. 2 seconds later to there. 3, 4, 5, and it will continue along. And so the amount that it actually moves is, well, it's arbitrary, but it depends on what the speed the ball is actually rolling on. If it's a very large speed, then the time it's going to move in 1 second is very large. If it's a very small speed, then the time it moves in 1 second is going to be pretty small. So that's not all that important in general. It's just the fact that it moves an equal distance in equal time intervals. Okay, so that was the horizontal movement. What about the vertical movement? Right? So this is really just going back to that, again, that linear motion, when we talk about linear motion, and specifically about accelerating downward. Right? So if you start out, you have a ball and it's not moving at all, and then you release it, gravity is pulling on it, so gravity is accelerating it downward, and accelerating means it's increasing its velocity. So it starts out at 0 velocity, and then gravity starts to pull it down. After 1 second, it will be moving at a certain speed, technically at 10 meters per second, because gravity is accelerating at 10 meters per second every second. So 1 second later, it will have moved a certain distance. 2 seconds later, it will have gone even further, again because it's accelerating, so it's going faster and faster in each of those time intervals. So in the first second, we move only this far. In the second second, we'll move that far because we're going faster. In the third second, we'll have gone that far because it's moving even faster. Fourth second, even faster. Hopefully you get the picture. So the actual distance that it travels after a given amount of time, if you remember, was given by this formula. The distance traveled is 1/2 the acceleration times the time squared. And again, the acceleration here is due to the force of gravity from the Earth. And that acceleration, I mentioned a second ago, is 10 meters per second per second. Yeah. That's not super important right now, but just to recall that this is where that vertical motion, that free fall motion is coming from. And we've talked about it before, so hopefully you remember. Alright, so putting that back together again, right? Now we're imagining taking that ball, rolling it off the edge of a table, and again that motion, once it gets off the edge of the table, and it can start to move vertically as well, not just horizontally, then we get a combination of horizontal and vertical movement. So remember that horizontal movement is moving equal amount of time, or equal distance in equal times. And that vertical movement is moving further and further every time interval. So right after so like at 0 seconds, say, the ball just leaves the tabletop. 1 second later, it will have moved horizontally the same distance it was moving before, whatever that horizontal distance is. And then it will also have moved vertically that same distance we talked about if it just dropped straight down. Right? So you combine those together, that horizontal movement and that vertical movement, and we get there where the ball is right there after 1 second. And again, I'm using an actual time interval, but the time interval is sort of arbitrary. If it was less than 1 second, then the actual distances might be shorter. But again, sometimes it helps to use actual numbers. So in 1 second, this is as far as it will move. And that also corresponds to the vertical distance I drew on here, even though this would be a very high table because it's at least 45 meters off the ground. So there's a little bit not to scale or anything like that, but hopefully you get the picture. If you don't, you better ask me questions about it. Right, so after 1 second, it moves this far horizontally, that far vertically. After 2 seconds, it'll move the same distance again it did horizontally, right? So another same distance horizontally, because that horizontal speed isn't changing. But again, vertically, it will have moved even further because it's accelerating downwards. It's moving faster and faster and faster downwards. Right? So the same movement horizontally, more distance vertically, we get down to where it is at 2 seconds here. And finally, after 3 seconds, it will have moved horizontally the same amount again, but now even more vertically. So we get all the way down here to that 3 second ball. Right? So that's why it's doing this sort of this arc. Technically this is we call it parabola. And in case you hadn't answered that question yet about which component gravity is acting on the velocity, right? You could draw the velocity of this ball at each moment, right? Right to begin with, just as it goes off the end of the table, it looks like this. After 1 second, it still has that same horizontal component, but now it has a vertical component, so the velocity kind of looks like this now altogether. And then after 2 seconds, it still has that same horizontal component, but it has an even larger vertical component, so now the velocity is kind of like this. Right? Keeps going along like that. Alright, so a question then. Excuse me. It's a good time for a question, I think. So, if you have, say, a cannon at the top of a tower, and you somehow set it up so that right as you fire the cannon, right as the cannonball leaves the cannon, another mechanism also drops a cannonball just off the back of the cannon, right, or off the side somewhere. So if you're able to set that up, and one cannonball is fired just as the other one is released and falls down, which one's going to hit the ground first? So take your second. Take your time and think about that. Hopefully give an answer. And ta-da, that was kind of a trick question. Because they're going to hit the ground at the same time. As odd as it might seem, that's just how it is, right? And the reason is because right when you release the one cannonball and you fire the other cannonball, right at that first instance, neither of them have any vertical velocity, right? They only have, this one has horizontal velocity, this one is essentially at rest just as you release it. It's not moving at all. So if it's going to move horizontal, or if it's going to move vertically, the only way they either of them change their vertical velocity is due to the acceleration of gravity, due to that force of gravity pulling them both down. And gravity acts the same on each of them. And again, just because this one has a horizontal component doesn't mean gravity acts any differently on the vertical component. Right? So this one keeps moving to the side, but it falls the same way that this one does. And I think we have a video of that. Right, so this is more of like a diagram of that happening. Right? If you release the red one, it's going to fall. And again, the way that its vertical movement is changing, or the way that its vertical velocity is changing, is just due to the acceleration of gravity. And the same thing goes for the vertical component of the fired cannonball, right? Just falling under the acceleration due to gravity. So yeah, so let's check out a video of this happening. So you see a couple different motions, pretty darn good, right? One goes off, one's released. You see this, the one being fired off is going to the side, but it's moving downward at the same, has the same downward motion. I'm not sure what that moving faster means there. Right, so as odd as it might seem, or as counterintuitive as it might seem, that firing something one way and then also dropping something at the same time, just because that one goes a large distance from you, doesn't mean that it's not dropping in the same way as the one you simply released. Okay, so what about projectiles not just shot off the end of a table or rolled off a table? What if you fire or release a projectile at an angle? Right, so going back to that original, like throwing a rock up in the air, or throwing a baseball, or tossing something underhand. So if you were to fire something and there were no gravity, then there would be no force that would change that object's velocity at all, and it would just continue going in a straight line. Right? That's Newton's, which one was that? One of Newton's laws of motion. That an object, I think it was the first one, the object in motion will just stay in motion unless acted on by an outside force. Right? So no gravity, no outside force, object's just going to keep going the way it's going. But since there is gravity, another way to look at projectile motion is essentially gravity is causing this object to fall the same amount as it would an object that you just released and let go. So we looked at, and even in the last slides, showed you exactly how much gravity, the distance gravity moves an object. Right? Gravity accelerates an object downward and it moves it more and more each time. And in the linear motion lecture, I believe, we looked at the actual amount of meters it moved, and in some of those last slides I had those meters on there, so they're on here too. So in 1 second, gravity will have moved a dropped object 5 meters, and in the second, it will have moved it a total of 20 meters. In the third second, it will have moved to a total of 45 meters. Right? That's what all those meter measurements were on the other slides too. So essentially, if you look at a shot object, or an object that's projected out, instead of going along that straight line, after 1 second, gravity will have pulled it down 5 meters. So instead of being up here, it's now down here. After another second, it would have gone all the way over here, but again, gravity pulled it down 20 meters. So it's actually back down here. After the third second, it would have gone all the way up there, but gravity pulled it down 45 meters, so it's all the way back down here. Right? So that's why we end up getting this arc. And again, gravity is only exerting a force on the a downward force on the vertical component of the projectile's velocity. So it's not changing the horizontal component. This cannonball being fired is still moving the same speed horizontally in the end as it was when it started, assuming air resistance is pretty minimal. And for a cannonball, it's pretty minimal. Okay, so I mentioned the term parabola a couple of times, but essentially that's just a name for the kind of arc that happens when you shoot something off, when you create a projectile. So the way that you get the full arc is, instead of just looking at something flying off of a table, we look at it when it first gets thrown up, and, well, in a very simple way of putting it is that the motion that it does as it's falling, on the one side we looked at in a lot of detail as it falls off the table, is the exact same motion, essentially mirrored, if you were to have thrown it up just to the tip of that table. So if you were to toss it up just to the tip of the table, then we get that same arc coming down. Right? So gravity is acting the same way the whole time. So if you throw it up, gravity is actually accelerating it downwards, so it's slowing it down. So that's why when you go from the first to the second to the third to the fourth, gravity is decelerating the object because it's moving upward. So it's slowing its vertical motion down. So in the first second it goes pretty far, but in the second second it will be going slower, so it won't go as far. And in the third second, numbers are a little confusing, but in the third second, it will slow down entirely and it reaches its peak right at the end, right? And then in the fourth second, we now have it coming back down. Gravity is actually increasing its speed downward now. And so we go a little bit distance, and then the next second, gravity is accelerating even more, so it's going even faster, we go further, faster, we go further. So we get this mirrored sort of thing. And, well, this is exactly what we would call a parabolic arc. Okay, so not to beat on this point too much, but it's going to be very important in a second. So just to remind you that if you throw an object, regardless of how you throw it, if you throw it straight horizontally, if you throw it upwards, throw it up at an angle, right? Gravity is acting on the vertical component of that velocity in the same way regardless of how you throw it. Which means that, well, if you throw it across, if you throw it upwards, instead of going the way that it would have gone, like in this picture, if gravity wasn't there, the ball would have just gone straight across. The person's throwing it straight out, so it would have just gone straight across. Instead, gravity is acting on that vertical component to accelerate it, to increase its velocity downward. And the result of that is that after 1 second, gravity will have moved, or increased its velocity so that it moves 5 meters down. There's no way around that. At least in, I said a bit about how gravity, the force of gravity, depends on how close you are to the mass that's creating that gravitational field, in this case the Earth. So the Earth's gravitational field is pretty constant all over the surface, and it decreases as you move away from the Earth, but you have to go pretty far before you get a noticeable change. So for all intents and purposes, it's the same anywhere you are on the Earth's surface, and even if you're on a very big cliff, it's still accelerating in the same way. So all that is to say that if you throw an object, in 1 second, gravity will have essentially pulled it down 5 meters. Okay, so why is that important? Well, that's only considering the vertical component of that object's movement. Like I said, gravity does not act on the horizontal component of that motion. So if you throw an object horizontally, it will go further and further depending on how much horizontal velocity you give it. Right? It's still going to fall the same way, but you can, the vertical movement, it depends on how fast you actually throw it. Right? So in this picture, you have somebody who's kind of just tossing a rock maybe off the side of a cliff here. So it goes, it has some vertical or horizontal velocity, it goes a little bit, and gravity's pulling it down, so it's moving downward, and so it does this little boop, just like falls off the side, right? So in each of these arcs is showing 1 second of movement of this projectile, right? So the first arc, the furthest to the left arc, is not a very large horizontal speed. Right? Just toss it a little bit. The middle arc is right, well, all right, you're going to give it a bit more horizontal speed, right? You're going to throw it a bit harder, so you throw it faster. So in that 1 second, when gravity brings it down 5 meters, it will have gone further horizontally because it has a larger horizontal velocity. You gave it more velocity when you released it. So we just kind of keep imagining giving that projectile more and more horizontal velocity. Right? So in the third picture, we throw it really, really fast, and so it goes really far horizontally in that 1 second, but again, it still falls down 5 meters. It still moves downward. You can't change that downward motion. So now we're finally getting to why this is all important, and that is because the Earth is not actually flat. Don't know if you know that. If you've been told otherwise, that is just not true. The Earth is curved, and there are many ways that you can see that the Earth is curved, but for one, well, we have satellites, and they utilize this exact idea, and that is the fact that if you go 8,000 meters horizontally, the Earth's surface will have dropped down 5 meters. Right? So this is a measure of the curvature of the Earth. If I could somehow take a stick, and an 8,000 meter stick, very, very long stick, well, something like a mile-ish stick, it's something like that, it's a very long stick, then, oh, I guess we also have it in miles and yards too, right? So over 5 miles, the Earth drops down 5 yards. So if you had a 5 mile long stick, completely horizontal, you stick it out and somehow manage to hold it up, somebody at the other end of that stick would see the stick would actually be 5 yards up in the air, right, the end of that stick. So that's how the Earth is curving, or that's how much the Earth curves. It's not a whole lot, which means it's hard to see on a sort of small scale, but it's definitely noticeable. And since I did bring it up, one of the easiest ways is you just watch a ship sail into the horizon. Because you end up seeing the very top of that ship last. The bottom starts to disappear, it's curving down, and eventually the ship disappears. So, if the Earth drops down 5 meters for every 8,000 meters you go across it, well, if I throw an object 8,000 meters per second, then remember in 1 second, that object's going to drop down 5 meters. So you throw this object 8,000 meters per second, very, very fast, 18,000 miles per hour, and in that 1 second, it will have gone 8,000 meters across, and gravity will have pulled it down 5 meters. But now the Earth has also curved, so the Earth has dropped down 5 meters. So just like in this picture on the left here, right? You throw it 8,000 feet, it drops 5 meters, but the Earth also dropped 5 meters. So it's no closer to the Earth, right? So this is where we start to get into orbits, right? So essentially, if you can throw something or get something to move that fast, then it moves far enough so that while it's dropping down under the force of the acceleration of gravity, the Earth is also dropping below it, right? It's curving away from it. So what happens if it drops but there's nothing there for it to land, right? Its horizontal component of velocity, assume there's no air resistance, so it's just going to keep going at that 8,000 meters per second. Then in the next second, it will go another 8,000 meters, it will drop down another 5 meters, but again the Earth will have curved down another 5 meters, right? So essentially that ball, or whatever that projectile is going to keep going, and in a way, one way to think about it is that it just keeps missing the Earth. It keeps falling towards the Earth, but the Earth keeps curving away from it at the same time. So if you did it at that right speed, it would go all the way around the Earth and hit you in the back of the head. In a cartoon sort of fashion. It probably did something else before that. And yeah, that's basically how orbits work. So Newton actually had this idea. They weren't able to achieve orbits at that time, but he realized the same sort of thing, that he knew the Earth was curved, he knew it was approximately the curvature, and so he could imagine that if you were at the top of a mountain, his idea was go to the top of a mountain and start shooting cannonballs or something like that off the top of the mountain, And if you could shoot it faster and faster and faster, then you'd start getting these arcs that would come out further and further and further, and eventually far enough that as it falls, it's falling in the same manner to match the curvature of the Earth, that it doesn't hit the Earth, it just keeps going around. Wild stuff. So last time we talked about rotational motion and circular motion, and now this is again an example of circular motion, that if you get an object going at 8,000 meters per second, it's going to keep falling towards the Earth, and it's going to keep missing the Earth, and it's just going to keep going around. Right? So it's going to keep going around a circle, and if you recall, to go for an object to continue moving in a circular path, there needs to be a centripetal force, a center-seeking force that points towards the center of that circle. Right? And that's gravity. Right? This satellite is now going around, and it's constantly being pulled towards the center of the Earth. So these pictures is like, you know, at any given point, if you imagine gravity just like disappears, then the whatever object is that's orbiting will follow a dotted line, right? And essentially what's showing is that that's the line that an object would keep following, but since gravity is there, it's kind of it's causing it to fall back towards the Earth, and so we keep getting into this, or we stay in this circular path. It's the effect of this centripetal force, which is the force of gravity, in this case at least. All right, so another question, two questions for you. So satellites, I'm pretty sure the term satellite just means an object in orbit, so satellite's a pretty broad term. But we have a bunch of satellites that do things like communications and GPS, all kinds of stuff like that. So satellites generally orbit at least at 150 kilometers, or about 100 miles above the Earth's surface. Right? So why is that? Is it because there is almost no gravity at that altitude? Is it because there's almost no air resistance at that altitude? So think about that for a minute and try to come up with an answer for those. So hopefully you didn't say there's no gravity at that altitude. If there wasn't any gravity, then there would be nothing to keep pulling the satellite back towards the Earth. There would be nothing to keep it going in a circle, right? So gravity is there, it's playing the part of the centripetal force. So it's not to do with the fact that there's no gravity. There is gravity there, and as we pointed out last time, at that height, that distance from the Earth, gravity again is weaker, but it's only about 10% weaker. Still about 90% the force of gravity, the acceleration of gravity we feel here is what they feel up there in orbit. There is almost no air resistance. This is the big one. So this is the reason that satellites orbit at such a height, right? Because again, like I mentioned before, or like I kind of touched on here and there, gravity is not affecting the horizontal component of that projectile's velocity. So you throw something really, really hard, it goes really, really far, and gravity pulls it down. Right? And I've said that essentially you're ignoring sort of air resistance, because that would be something like, it's a kind of friction would act against the motion of the object, and it would slow the object down. So it would actually change the horizontal component of the object's velocity, or that satellite's velocity. And you would want that, right? Because again, we need the object to be going at least at 8,000 meters per second, so that in that 1 second, it will fall down 5 meters, but the Earth also curves 5 meters. Right? And if you slow down more than that, then we're getting back to the case where it goes, you know, it falls down 5 meters, but it will only have gone less than 8,000 meters now. So it's actually getting closer and closer. It gets closer to the Earth and eventually crashes back into the Earth. Right? So we need to go at least that 8,000 meters per second, and it makes it much easier to maintain that when there's just very little air resistance. So up at 100 miles above the Earth's surface. There's very little air, there's very little air resistance, so you really don't need much to keep an object going at whatever velocity you get it up to. There is some air resistance, so that's why satellites and things will have thrusters, so they can basically expel some gas in one direction and speed themselves up a little bit to keep going at the rate that they need to be going. All right. So I've mostly just been talking about circular orbits, right? Perfectly circular orbits. And that is that if you get at that exactly at that 8,000 meters per second, then you're going to be in a perfectly circular orbit. Very difficult to get an exactly perfectly circular orbit. Anything less than that 8,000 meters per second means, like I said, you're going to crash eventually back to the Earth. But if you go more than that 8,000 meters per second, it turns out you still can be in an orbit, you just now are in an elliptical orbit. So instead of being at a constant distance from the Earth and constantly falling the same amount and constantly missing the Earth because it's curving away from you, you're in an elliptical orbit where at some points you're closer and some points you're further away from the Earth. And this is what you get for speeds that are higher than that 8,000 meters per second or 8 kilometers per second. So this is a little bit more detail about elliptical orbits. This is not something that I really expect you to get in detail, but I think it's interesting to note, so I'll talk about it for a minute. And that is that in a circular orbit, the force of gravity is always pointing towards the center of the Earth, right? That's always the force of gravity. And in a circular orbit, the velocity of the object is always tangent to that circular orbit. Right? Meaning that the force that's acting on that satellite or on that orbiting object is always perpendicular to its velocity. So its velocity is going this way, the force is going down. Its velocity is going down, the force is going this way, right? The force is always perpendicular to the velocity. So that is to say that the force is only causing the object to turn. It's not changing its velocity. It's not changing its speed, right? The length of that velocity vector. However, in an elliptical orbit, it's no longer the case that the force is always perpendicular to the velocity. So that means that objects in elliptical orbits actually speed up and slow down. They're not moving at a constant rate. Right? And we can see that by just looking at a couple of positions that the object is in, look at its velocity vector and see the direction the force is acting, and we can see that that force is going to cause an acceleration that will actually affect that velocity. Right? So on the left-hand side, right, if you have an object in an elliptical orbit at that position, the velocity is always tangent to that elliptical orbit. So like at that point it's just upward, but the force is always pointing towards the center of the Earth. Right? So the force there pointing towards the center of the Earth, if we look at the components of that force, right, again draw that vertical wall, project onto the vertical wall, that's the vertical component of the force, draw the horizontal sort of floor, in this case the force is below it, so we project upwards here, but that's the horizontal component of the force. And again, horizontal and vertical components are independent, so the horizontal component of the force is not going to affect that velocity. It's not going to change the speed of the object. It's not going to cause an acceleration vertically. It's just going to cause it to turn. But there is a vertical component to that force, right? And it's in the opposite direction of the velocity, so it's decelerating the object. It's causing acceleration in the opposite direction of the velocity, meaning it's slowing the object down. Right? It's like it's pulling on the object as it tries to move away. So at that part of the arc, the object's actually slowing down. Right? And then it gets all the way up to the top of this arc, and the velocity again is still tangent to the ellipse, and now the force is straight, the force is always towards the center of the Earth, it's going straight downwards. Now we have a situation just like a circular orbit, where here's the velocity, here's the force, they're perpendicular, the force is not going to change the speed of the object. Right? All it's going to do is turn the object, just like in a circular orbit. But then again, we get all the way back down to some place like here, like the sort of mirror side from the beginning, where now you have velocity straight down, you have a force still again going towards the center of the Earth, and you look at the components of that force. There's some down, there's some to the left. So the left one, again, is just causing the thing to turn, it's not changing its speed at all. But now we have a force that's in the direction of velocity, that's going to cause an acceleration, that's going to speed the object up. So what happens in elliptical orbits is you get this like slowing down, slowing down, slowing down, speeding up, speeding up, speeding up, speeding up, slowing down, slowing down, slowing down, speeding up, right? So it's constantly changing the actual velocity of the object, or the speed of the object. Yeah. All right, so the last thing just to talk about quickly here is, well, basically just, keep moving past further at faster and faster speeds. What happens to these projectiles, right? So if you throw something horizontally and you don't throw it that fast, it's just going to fall to the ground, right? If you throw it much faster, it's going to go further, but it's still going to hit the ground eventually, right? If you throw it fast enough, you get it up to that 8,000 meters per second, then it's falling towards the ground, but the ground is curving away from it, and so it misses the ground, and you get this circular orbit. If you throw it beyond that 8,000 meters per second, above that 8,000 meters per second, then we get to those elliptical orbits, right, where it's no longer just in a circle, and it actually slows down, and then speeds up, and then slows down, and then speeds up, and this is what the Earth and the other planets are doing on the Sun, too. And essentially, there's a whole range of elliptical orbits. You just go above 8,000 meters per second. But it turns out once you get up to about 11.2 kilometers per second, or 11,200 meters per second, that's where we hit what's known as the escape speed, right? Or escape velocity, or it's an escape trajectory. So essentially what happens is you've thrown it fast enough that it's moving away from the Earth, and the Earth is pulling it back, but it's not pulling it back fast enough. And actually, as it moves further and further away from the Earth's gravitational pull is getting less and less and less too. So it's moving further away and it's pulled back to the Earth, but it's pulled back less and less and less, and the Earth's pull is less and less and less. And if you reach that 11.2 kilometers per second, it's fast enough that it's not going to come back to the Earth at all. It's just going to continue to go and leave. So that's what we call the escape speed, or the escape velocity. And essentially anything beyond that is technically what we call a hyperbolic trajectory. And a lot of asteroids, or not asteroids, comets, like interstellar objects will have these sort of hyperbolic trajectories, where essentially, like Halley's Comet or something, will come in very, very fast and kind of wrap around the Earth and then shoot all the way back out. So there's no sense that it's ever stuck in the Earth's gravitational well, it just kind of flies in and flies back out. So it's well beyond the escape speed, and it never gets trapped in the Earth's gravitational pull. Yeah. Cool. So that's it. That's all I got for projectile motion, and that means that's all I got for mechanics. That is the end of part 1 of this course. The longest part of the course, by the way. The other parts are a bit shorter, but there's a lot to go over here. So I hope you enjoyed these and rewatched if you were confused, and sent me questions if you had any questions, or kind of the office hours, all that good stuff. And I guess good luck on the test, the exam. See you later.